We have thus come to the last section of this second chapter, that is the last section on group theory, and this one involves finite abelian groups. And the first result in this section is this one, Theorem 214.1, which states that every finite abelian group is a direct product of cyclic groups. If we want to be more specific, we should say every finite abelian group is a direct product of finitely many finite cyclic groups. Now, because we have defined direct products only for finitely many groups, so when we say direct product, it's understood that only finitely many groups are involved. But of course, we will see that the cyclic groups that we will get here after proving the theorem are also finite. Alright, so now we have to see the proof. Now the proof as given in the text starts with a discussion. Basically, the proof involves choosing some elements which have maximal order in some sense. But that discussion, whose aim of course is to simplify the proof, is to make us better understand the proof, in fact makes it more confusing, unfortunately. So we won't go through the discussion. We will straight away go through the steps of the proof carefully, checking out the discussion. And the proof is a little, I won't say complicated, but it's a little heavy. Like there are many steps, and at times it's not really very clear why we are doing something. Only much later, when we achieve what we are trying to achieve, then only we understand that, because of this we started our calculation like that. So that's why I have decided to divide the proof into 3 stages. 3 stages means actually these are not stages in the proof itself, but today we won't see the entire proof. We will see only the first part of the proof, which is not an actual part in the proof. It has nothing to do with the proof, but we will go only that far. Okay. And in other coming videos, we will see the other parts. So let's see what this so-called first part has, which is what we are going to see about the proof today. Alright, so in the beginning itself there is a simplification. I mean, it's given that we have a finite abelian group. Now the order of a finite abelian group is, of course, it has its own factorization. There is in fact one case which you can handle in the beginning itself. Say G is a finite abelian group which has only one element. G is a group of order 1. Then of course it's the trivial group having only the identity element, and the claim here is trivially true because G itself is cyclic. It's a finite cyclic group and it's also a direct product, and in this product only one group is involved, and that is why we can assume that order of G is greater than 1. Now, being a positive integer greater than 1 by the fundamental theorem of arithmetic, this has its own prime factorization. However, because of exercise 5 from section 213, it's enough if we consider only this case where the order is actually the power of some power of a single prime. Now, exactly how this simplification is achieved, for that I urge you to go to exercise 5 from section 213, okay, and then try to understand why that is the case. So we will start with this. So accordingly, let's start the proof itself like this. Due to exercise 5, section 213, that means the previous section, which as direct products. It's enough to consider the case this. I should have actually started by writing let G be a finite abelian group. I haven't done that, I have forgotten. So you please write that here. Before writing this line, you write let G be a finite abelian group. And then you write, due to exercise this, it's enough to consider only that case. Where, let us further write where simply writing P is not enough. We have to also say that P is a prime. Where P is prime and n belongs to the set of natural numbers. Keep in mind that in this book, n does not contain 0. Now, for some of us, 0 is not a natural number. But in some books, 0 is considered to be a natural number and is considered to be an element of that set n. Now, whether you call 0 a natural number or not actually does not make any difference. It's just a way of for some people it's convenient to also include 0 in the discussion that they are having along with the other positive integers. So they can call those things collectively the set of natural numbers. But for some people, 0, it's not really, it does not serve any purpose by calling 0 a natural number. So that's the case here. For us, 0 is not a natural number in this book. And that is why this set consists of all the positive integers. So when you see something like this in this book, you have to understand that n is a positive integer. And the reason is also clear, because if n is 0, n of course cannot be negative. If n is 0, then we are back at this case, which we have already discussed. Alright. Now, we will start the proof by considering an element in G of maximal order. Let A1 in G be of maximal order. Why would such an element exist? That's the first question. You see, G is after all a finite set. So every element in G must have finite order, because G is a finite group. And that is why there may be multiple elements having maximum possible order. And that is why such an element A1 exists. A1 is one of them. And by one of the corollaries to Lagrange's theorem, that order will look like this. Because the order of any element has to divide the order of the group, and that's why it also has to be some power of that same prime P. Further, this n1 is less than or equal to n. Let's write that also, where n1 is a non-negative integer, of course, and is less than or equal to n. Okay. And we are also going to now consider the cyclic subgroup of G generated by this element, and call that subgroup, say, capital A1. Yes, and let A1 be the cyclic subgroup generated by small a1. So in the very first step, we have considered an element in G having maximal possible order. But now we are going to consider another group, the quotient group of G pi A1. Keep in mind that G is abelian, so A1 of course is normal. Any subgroup of an abelian group is normal, so we can consider the quotient. Now, and in that quotient group, again, we will consider one element having maximal possible order. Say that element is B2 bar, and because the elements in G slash A1 are cosets of A1 by some elements of G, so this B2 bar in fact is a coset of A1, so given by the element B2, which is some element of G. And this is also not just any element, but an element of maximal possible order. Let this be of maximal order. Again, what type of number will that order be? You just try to see what the order of this quotient group is. N minus n1. So it's again some power of p. So this order also, due to that one corollary to Lagrange's theorem, has to be some power of that p again. Say p to the power n2. Now note that just like this inequality, there will be one involving this one and this one, and n2 will be less than or equal to n minus n1. However, we are not interested in that. We are interested in something else, namely an inequality linking n1 with n2 itself without having n. And as I said before starting this proof, it's not immediately clear why we are doing these things. It will become clear only much later. Alright, now let us recall an exercise that we have already solved way back when we were studying, I think, homomorphisms, normal subgroups, those things. At that time we came across one exercise which says that the order of this coset will divide the order of B2, the element by which we are forming the coset. And from that relation, we will have this next thing. Since order of B2 bar divides the order of B2, and the relevant exercise where we proved this is this. See exercise 15 of section 626. 6, I think it's that section which treats homomorphisms. Okay, because of this, and note that B2 is an element of G and A1 is an element of G having maximum possible order. So order of B2 will be less than or equal to the order of A1. And order of P2 is less than or equal to the order of A1. You see, this order dividing this order means what? In particular, it means that this is less than or equal to this. what is this? P to the power n2. And this in turn is less than or equal to this. And what is this last one? P to the power n1. So ultimately we can conclude that P to the power n2 is less than or equal to P to the power n1, and that happens only when n1 is less than or equal to, n2 is less than or equal to n1, because n1 and n2 are both non-negative integers, that's why. So we have n2 less than or equal to n1. This way we have obtained an inequality involving only n1 and n2. Okay. Now note that it's a bit difficult to remember the steps. And also it's really somewhat difficult to see at once where this proof is going. But anyway, let's just go with the flow and see where we end up. Note that a1 b2 to the power p to the power n2. So you see here we are looking at a coset of a1 by the element which is the power of b2, where the exponent is p to the power n2. a1 b2 to the power p to the power n2. This of course by the definition of the binary operation in this quotient group is a1 b2 to the power p to the power n2, and a1 b2 is simply b2 bar. P to the power n2 is simply the order of this element. So this will be the identity element, but of which group? Of this group. So a1. And from this first and last term of these equations, we get b2 to the power p to the power n2 belongs to a1. Okay, so this particular power of b2 is an element of a1. But can a smaller power of b2 also be an element of a1? Smaller positive power, say. Suppose that b2 to the power I belongs to a1 for some I satisfy, for some integer I of course, understood. There is no need to again write that, okay. It's understood from the context that here I denotes an integer, strictly less than p to the power n2. Actually something will go wrong with this supposition. But what? Then what? Then let's carry out a calculation like this, but this time with I. Then a1 b2 to the power, okay, we can start with, in fact, b2 bar itself. That way it will become more clear. a1 b2 to the power I. This is equal to a1 b2 to the power I. But because b2 to the power I is an element of a1, so this coset is nothing but a1. However, something has gone wrong here. Why? You see, the order of b2 bar is p to the power n2. So no smaller positive integral power of b2 bar can possibly be equal to the identity by the definition of order, by its minimality. That has gone wrong. But this contradicts the fact that the order of b2 bar is p to the power n2. So no such I exists. always remember when going through a proof, no, it does not matter how silly an argument looks or how insignificant a step looks. If it is not clear to you, you should always try to prove it rigorously. But this contradicts if you suppress steps and try to show off by showing that I know so much that I need not write all the steps, that doesn't look good actually. Writing all the steps clearly, in fact, makes it look good. But this contradicts this statement, p to the power n2. So, p to the power n2 is the smallest positive integer such that b2 to the power p to the power n2 belongs to a1. Okay, this much we have established. Okay, so the smallest nature of p to the power n2 has been proved. Now, however, we concentrate on the fact that this is an element of A1. And what is A1? A1 is the cyclic group generated by small a1. So, this element will also be a power of small a1 for some exponent. Let that exponent be I. Now, b2 to the power p to the power n2 is a1 to the power I for some I belonging to j. Capital J, do not forget, in this book means the set of integers. It's not as, I don't think it's a standard notation. The standard notation, of course, is this. This is how we denote the set of integers, where Z stands for the German word Zahlen, for numbers. But anyway, here by capital J we mean the set of integers. Okay, now with this what do we do? So, now what we do, now let us calculate this power of a1 to the power I. P to the power n1 minus n2. Note carefully that here n1 minus n2 is a non-negative integer, and that is why this is not a fraction. This is itself an integer, and that fact is coming from this inequality. So it makes sense that we can consider this. What shall we get? This is after all what? b2 to the power p to the power n2 whole to the power p to the power n1 minus n2. Because different levels of exponents are involved, so you have to write rather carefully. Keep some space, okay, some vertical space between lines. If you run out of space and then later misinterpret this, everything will go down. Now, by one of the two rules of exponents, and after a little calculation, we get this. You understand why that happens. And this is equal to the identity. This identity E is, of course, the identity of our original group G. But why is this equal to identity? Note that, of course, p to the power n1 is not the order of b2. We don't know what the order of b2 is. We only know that the order of b2 bar, a1 b2, is p to the power n2. And this is the order of a1, this element, maximum possible order. However, the reason for this to be E is that since p to the power n1 is the maximal order of elements in G. So x to the power p to the power n1 is always equal to E for any element x in G. However, this itself may be a little confusing. Why is this true? Let's see. You have x to the power p to the power n, right? Note that you can write the exponent like this. X to the power order of x, you see, x being an element of capital G will have its own order. After all, we are in a finite group, so this is a positive integer. Plus minus this, okay? And this gives us what? I think, okay, hold on. Actually, this is not why we will get this equal to E. See, I also got confused. This is why each and every step has to be carefully analyzed. Why are we going to have this though? If I fail to provide an explanation here, that means there is something wrong. Oh yes, the nature of the orders in this group makes this happen. You see, simply taking order of x is not enough. Order of x, after all, is also some power of p. Say p to the power something, say m. Now, can this m be greater than n1? Of course not, because otherwise p to the power m will be greater than p to the power n1. But then the maximal possible order is exceeded by the order of x. But then it is not maximal, and that is why this cannot happen. So m has to be less than or equal to n1. Now, because of this, we should attack the exponent of the exponent, not the exponent itself. Here itself you write m plus n1 minus n. Okay? And now, now it will come, see? This can be written as this, okay? And this, by one of the rules of exponents, is this. Now, what role does this inequality play here? You see, the fact that n1 minus m is a non-negative integer makes this power an integer. Otherwise, if it was negative, this would not be an integer. Okay, but fractional powers of group elements are not in general defined. So that's why here we are, it's okay. But this is E, because p to the power n is the order of x. And that is why this is equal to E. So you see, even in this statement itself, there are many things. But now you know the reason. So if you want, you can also include this part. Or you may also not include this part. If you feel that it's just too easy to include, So this is the reason. Now looking at the first term and the last term, we have this. So, and using the rules of inequality, this itself can be written as a to the power I times p to the power n1 minus n2 equal to e. Hence, by a previous exercise, the order of a1 has to divide this exponent. Thus, I think it is exercise 36 of some section that tells us that when you have an equation like this, then the order of the base divides the exponent. Which section I don't remember. It is probably one section where there are many exercises. But anyway, so we just write this. Thus, order of a1 divides I times this i.e. but what is order of a1? It is p to the power n1 minus n2. This implies p to the power n2 has to divide I. Again, if you cannot at once see why this is true, then write everything in detail. Since, okay, p to the power n1 dividing this integer means what? It means that this integer is an integer multiple of p to the power n1. That's why we write since I times p to the power n1 minus n2 is some multiple, say alpha times p to the power n1 for some integer alpha. Because of this, now what you can do is you can divide on both sides of this equation by p to the power n1 minus n2. When you do that, you will get this I is equal to alpha times p to the power n2, and that is why p to the power n2 divides I. Alright. So p to the power n2 is the largest integer for which the corresponding power of b2 belongs to capital A1. But at the same time, we have also got this. And this, what is this I? This I is that exponent which gives us this power of b2 as a power of a1. And that I, it turns out, has to be divisible by p to the power n2. Okay. So if it is divisible by p to the power n2, it will be some multiple of p to the power n2. Let I be equal to p to the power n2 times j, where j is some integer, some positive integer actually. Is it necessary for j to be positive integer? Well, that is not our something that we should be concerned about. J is some integer, that's what matters. All right. Okay. So, now that we have something to write in place of I, let's see what happens to b2 to the power p to the power n2. It is a1 to the power I, and that now becomes a1 to the power p to the power n2 times j. And now we are going to consider a new element and call it A2. That's why we were adopting the name B2. Actually, we need a sequence of elements A1, A2, A3, but choosing those things takes some time. So now we can choose an element A2, and that A2 will look like this. Thus, if, let me write it here, A2 has to be chosen from this equation, and A2 is A1 to the power minus j times B2. This j was needed. That j we did not have previously. Now only we have j through I and p to the power n2. If we call this element A2, you see, we can take, of course, minus j, because taking powers of group elements where the exponents are negative is allowed. However, fractional exponents are not allowed in a general group. So, for this element, then something can be written. Then A2 to the power p to the power n2 becomes what? Let's use the definition of A2. A1 to the power minus j B2 whole to the power p to the power n2. And because we are in an abelian group, the exponent gets distributed like this. And then again, using rules of exponent and doing everything, we get this. So you see, b to the power p to the power n2, of course, we have here, but on the other side we have this thing, and it's just the corresponding power of that same thing, or in fact this is just the inverse of this, because we have minus, and hence this is e. And from this we can say something about the order of A2. You see, this power of A2 has become identity, but can a smaller positive integral power also becomes identity? If there is no such smaller power of A2 which becomes identity, then the order of A2 will be equal to p to the power n2. That is our aim. So suppose we take a smaller power and set that equal to identity. A2 to the power s is equal to identity for some positive s that is less than p to the power n2. Then something goes wrong. What goes wrong? Let's see. Then what happens to b2 to the power s? In place of b2 to the power s, you can write a1 to the power js times a1 to the power minus js times, this 2 will give us identity b2 to the power s. Again, because we are in an abelian group, so this becomes a1 to the power minus j times b2 whole to the power s, and this is a2 to the power s. All right, and that becomes what? Oh, so this becomes identity, and we are left with a1 to the power minus js. However, this is a power, an integral power of a1, where the exponent is minus js. So it belongs to the cyclic subgroup capital A1. All right, but Then what have we achieved? Here we see that this positive integral power of b2, where the exponent is s, belongs to a1. However, s is less than p to the power n2, and this has violated something, namely the fact that p to the power n2 is the smallest positive integer. That gives the corresponding power of b2 as an element in a1. So that smallest nature of p to the power n2 has been violated here. This, and I just simply write this is a contradiction. Or if this seems a bit too little of an explanation why this is a contradiction, you can write this is a contradiction to the minimal nature of p to the power n2. And that is why no such s exists, or in other words, p to the power n2 is the smallest positive integer for which the corresponding power of a2 is equal to e. But then by definition of order, the order of a2 is equal to p to the power n2. So we write that as conclusion. Hence, order of a2 is equal to p to the power n2. And now using this element a2, we are going to consider the generated cyclic subgroup. Just like using a1 we generated capital A1, and using a2 we are going to generate capital A2. Let capital A2 be equal to the cyclic subgroup generated by small a2. Okay, now the next thing we have to see is that the subgroups A1 and A2 intersect trivially. This is the next thing we want to prove. So for that, let us consider a common element, common to both A1 and A2. Now, because A2 is being generated by A2, any element of capital A2 will be some integral power of small a2. So if there is an element common to A2 and A1, that element will look like an integral power of small a2. So that's why we take this. Say the exponent is t. Say this belongs to A1. Already its form makes it an element of A2. Now suppose that it belongs to A1 as well, where t is an integer. Okay. Then what can we say? Then using the definition of A2, that is this A1 to the power minus j times b2 whole to the power t belongs to A1, or A1 to the power minus jt times b2 to the power t belongs to A1. However, this power of A1 already belongs to capital A1 because capital A1 has small a1 as a generator. So we can further write or b2 to the power t belongs to A1. But again, the smallest exponent for which the corresponding power of b2 belongs to capital A1 is p to the power n2, smallest positive exponent. Okay. And that smallest nature of p to the power n2 makes t divisible by p to the power n2. Let me show you how, or you may stay confused here itself. This implies let me first write the conclusion and then I will show you how. This implies that p to the power n2 divides t. Now an explanation for this divisibility. So by the division algorithm, or what we may call Euclidean algorithm, t can be divided by p to the power n2. So there exist integers, say mu and nu, quotient and remainder, such that t is equal to mu times p to the power n2 plus nu, where nu is non-negative and less than p to the power n2. Nu is non-negative and less than p to the power n2. I think I have almost run out of ink. Let me just put some more. So do you see how complicated? I don't really want to use the word complicated, but the proof is a bit lengthy and it's a bit all over the place. It's going this way and that way without becoming clear why it is doing so. That's why it's smart to only see chunks of the proof at a time. And this is the first chunk. Okay, so this is the quotient mu and this is the remainder nu when we divide t by p to the power n2. What does that give us? Note that b to the power t then b2 to the power t then becomes b2 to the power mu times p to the power n2 plus nu. Now using the rules of exponent, you can write this as b2 to the power p to the power n2 whole to the power mu times b2 to the power nu. Hence, b2 to the power nu is equal to b2 to the power t times b2 to the power p to the power n2 to the power minus mu. Okay, now look carefully. b2 to the power t belongs to capital A1 and b2 to the power p to the power n2 also belongs to capital A1. In fact, p to the power n2 is the smallest positive exponent for which this happens. But after all, these things are elements in capital A1. And that is why this product will also belong to A1. That means b2 to the power nu is an element of A1. Now nu is non-negative and less than p to the power n2. Can nu be positive? No. The minimal nature of p to the power n2 as the minimum positive number for which that power of b2 belongs to A1 forces nu to not be positive. That is why the minimal nature of p to the power n2 forces this conclusion that nu has to be equal to 0. But if the remainder is 0, then of course there is a complete divisibility, or there is simply divisibility. That's how we are getting this. Okay. Now let us continue. Since order of A2 is equal to p to the power n2. This implies that the tth power of A2 to the power t is equal to e. Why? That's because you see p to the power n2 divides t. So let me write the explanation here. T is equal to something, say beta times p to the power n2, where beta is an integer. So A2 to the power t will be, if I write at once using one of the rules of exponents, this. Then what do we get? Order of A2 is p to the power n2. So this is identity. And that's how we get identity. So this element of capital A2, which was any element of A2, which we have considered to be in A1, must be equal to the identity, nothing else. Thus, the only common element is identity, and that is why the intersection is trivial. That's what we wanted to show. And one last thing, one more thing, this t may be negative. Okay, we don't really know, because this is any element of A2, so t may be negative, and we don't care. You see, here the smallest positive nature of p to the power n2 only has been used. T may be positive, may be negative, may be 0 also, we don't really know or care. Mu also can have any sign. And hence, so if we have got two subgroups which intersect trivially, then the order of their product is just the product of their orders. Actually, it's also divided by the order of the intersection, but that is 1 in this case, and that is why. And so, order of A1, A2 is equal to order of A1 times order of A2. That is equal to, of course, this. And this is where the first chunk of the proof, as I have divided it up, ends. Actually, in our attempt to show that G is a direct product of a finite number of finite cyclic groups, we have got two such cyclic groups, A1 and A2. And the next thing, of course, would be to consider, or choose A3. How that will be chosen, that we will see in the coming videos. So that's just it for tonight. See you in the next upload. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.